Level cuts can be precise when done where the slope is steep. If the slope is gradual, they're not as precise. But they're highly vulnerable to errors in the index of refraction and the photometric calibration. POEM strategy and the two strategies that we'll talk about with turning points will be compared. So I've probably said most of what I have to say about these. Now let's look at the effect of noise. This is only 0.3% full-scale noise. So it's not too bad. I've blown this up 7 times here, and my scale divisions are 0.3%. So you can see this is RMS, or plus or minus 0.3%. So that's a feel for what we're talking about. Now this turning point technique using 5 points is a case where anytime I'm coming up and the slope changes, then I'm near or at a turning point. For example, if I were to say anytime the slope changes after 1 point, then this one would be an indication that that's the turning point. But if I take 5 of them, then I've got to have 2 that are lower than the highest one before I would say, okay, I've got a turning point. And of course, if there's no noise, this is perfect. But if there is noise, you can see that the noise influences it. And so this will tend to cut before it gets to the actual turning point a little bit. And then if I go on, these would be my data points. I've done work with the telemetrics people in Scotland who make a monitor that one can buy. And there are a lot of these around the world. And one of their preferred cut techniques is this type of a cut technique. And of course, when the noise is small, they take what noise they have and run it through a filter. So they're getting a much smoother curve in this. And so their turning point cuts are generally quite good, but are limited in principle. My approach to many things is to, if I'm interested in this durability of an automobile, I can imagine I'd like to take it out on the salt flats in Utah and push it pedal to the metal and see what breaks. So philosophically, that's what I tend to do, is take something to its extreme to find out its behavior characteristics. So this is an extreme case of noise I'm illustrating here. The other approach is to try and match a parabola to this. And if you look at the sine curve and the parabola in a certain region here, they're virtually identical. So a turning point would be found there. If I can fit my data to the parabola, then I can find that pretty accurately. If I found a turning point, I could specify, for example, a certain distance after that, either crystal distance or optical distance. This would not be using that POEM, but just saying I come past, I find this, some crystal reading for that, and then add crystal to it to cut, or I find what level that is and I cut. Actually, if I'm doing the POEM, of course, I don't need to find the turning point. I just need to find the minimum here and the maximum here, which will be the real minimum plus whatever noise I've got. But that's not a big deal. So this Parabolic Fit, I wrote a program that's philosophy is this. I start out somewhere early in the layer, and I take 3 samples, 3 points in a row. And in principle, if there's no noise, then 3 points define a parabola, and I know exactly where this point is. But there is noise. So what I essentially do is I keep this piece of data, and I keep moving this point up and this point halfway in between. So when I get up to here, I've got this point and that point and this point, and now the fit is quite good. So it's kind of like the wheelbase of a car. If you got a short wheelbase, you'll bounce around a lot, but you got a long wheelbase on your Cadillac limousine, it's a pretty stable ride. So that's the philosophy of that, and here's what it looks like when you start out with just the 3 points close together. It's quite noisy. And as I get more and more wheelbase, it gets quieter and quieter. And I get down to the prediction of where the turning point would be. So this is the current point in my taking data points. This is just the count of 35, 36, 37, etc. And this is the prediction from those 3 points, which is way off here and gets better and better. And when the predicted turning point matches the current point, that's the turning point. And so this is pretty insensitive to noise and works good in the simulation.